Siberia, the Yenisei River, and a dam so powerful it once turned a 900-ton turbine into a weapon. Deep in southern Siberia, curved into a narrow canyon of the Yenisei River, stands the Sayano-Shushenskaya Dam, a true joint of hydropower engineering. Stretching 1066 meters across the river, this is an arch-type dam, a design that doesn't just resist water, it redirects it. Instead of fighting the immense pressure head on, the dam transfers that force sideways into the solid canyon wall. This is its cross section. A towering height of 242 meters, almost the size of a skyscraper. At the base, the concrete is a massive 105.7 meters thick, built to withstand enormous load. And at the crest, it narrows down to just 25 meters, optimizing material while maintaining strength. And behind it, water builds up with tremendous energy. That energy feeds a powerhouse with a total installed capacity of 6,400 megawatts, making it one of the most powerful hydroelectric stations in the world. And at the heart of these systems are Francis turbines designed for high head operation. Water falls from a height of up to 220 meters with a rated operating head of 194 meters. Each turbine handles a massive flow up to 360 cubic meter per second. First of all, what does 1 meter cube per second mean? A cubic meter per second is a unit of flow rate. It means 1 cubic meter of water passing a point every second. Take a cube that is of 1 meter height, 1 meter width, and 1 meter length. That's the entire volume flowing past every second. That's a huge amount of water in motion. Now convert this into gallon. 1 cubic meter is equal to 264.17 US gallon. And if one turbine handles up to 360 meter cube per second, that means this is 95,100 gallons per second through a single turbine. This flow strikes a runner 6.25 meters in diameter, equipped with 16 precisely engineered blades. The runner alone weighs 156 tons, spinning to 142.8 rpm. Each unit can generate up to 735 megawatts with a rated output of 650 megawatts. And above the turbine sits the generator, an umbrella type generator with a single guide bearing positioned above the rotor, designed for stability under extreme load. Inside this generator are 42 poles generating electricity at 50 Hz, but the real scale is almost unimaginable. The rotating part alone weighs 900 ton. The stator adds another 500 ton. This is not just a machine, it is a control force of nature. And when something this powerful loses control, the results are beyond catastrophic. Let's start with the basics, just like many of you suggested. Once the intake gate opens, water begins its journey. It rushes through the penstock, carrying enormous energy, and reaches the turbine. But it doesn't hit the turbine directly. First, it enters the spiral casing, flowing radially around the runner. Then comes the wicket gate, precisely controlled blade that regulate both the flow and the angle of the water. As these gates open, they guide the water perfectly onto the turbine blade, causing the runner to spin around its axis. After transferring its energy, the water exits axially through the top tube and flows back into the river. Now that spinning motion is powerful, but rotation alone doesn't produce electricity. The turbine shaft is connected directly to the generator rotor, and this rotor is supplied with an excitation current, creating a strong magnetic field. As the rotor spins, this magnetic field rotates inside the stator, and that's where the magic happens. The moving magnetic field induces electric current in the stator winding, and electricity is generated continuously and at a massive scale. Construction of this dam begins in 1963. The first unit came online in 1978, and the plant became fully operational by 1985. The incident at this plant was caused by turbine number 2, a unit that had a long history of instability, excessive vibration, and frequent mechanical issues. But to understand what went wrong, first let's talk about a paperclip. Bend it once, nothing happens. Bend it again and again, and eventually the clip will break. That's a simple example of metal fatigue and stress. Everyone has seen a washing machine during its spin cycle. During its spin cycle, if the load is even slightly imbalanced, it starts to vibrate violently, shaking the entire machine. Now we need to understand the operating band of this turbine. See, hydropower turbines operating under high head conditions have a very narrow, efficient, and stable range. Outside this range, hydraulic instability begins to develop, caused by flow pulsation and water hammer effect, leading to vibration and long term structural damage. So, for this dam, on the incident day, the dam was operating at 212 meters. At the head of 212 meter, the turbine operates within four distinct bands. Band number 1 0 to 265 megawatt, which is the allowed band. Band number 2 ranges from 265 to 570 megawatt load, that is not recommended zone. And band number 3 is 570 to 640 megawatt, that is recommended operating range. Now there comes the band number 4, which is above 640 megawatt, that is forbidden. Okay, now let us talk about the history of turbine number 2. Turbine number 2 had been problematic almost from the beginning. 1979 first issue appeared after installation. 1982 1983 persistent problems with seals, short vibration, bearing, and in 2000 a major overhaul revealed serious damage. So cavities up to 12 millimeter deep were found in the runner. Cracks up to 130 millimeter long on the runner were repaired, along with multiple bearing defect. So further repairs again were carried out in 2005, but similar issue reappeared, indicating chronic structural and hydraulic problems. By January to March 2009, the turbine underwent scheduled repair, modernization, and then installation of new electro-hydraulic speed regulator. So during the 2009 overhaul, cracks were again found on the runner blade, which were welded. But here comes the problem: the turbine after the repair was not properly rebalanced. Okay, so this led to increased vibration 0.15 mm at full load, already higher than normal vibration level compared to other units. Also, by July 2009, vibration level exceeded the allowable limit, continued increasing at an accelerated rate. So, on the night of 16th to 17 August 2009, keep in mind the 17 August 2009 is the incident day. So, vibration level rose significantly. The turbine load fluctuated repeatedly. First of all, 600 megawatt, that is band number 2 recommended. Then load eventually drops to 100 to 200 megawatt, band 1 allowed, and it frequently traveled between 600 to 200 megawatt again and again. Okay, throughout the night the turbine cycled between 10 megawatt to 610 megawatt. This load fluctuation created massive surges, leading to excessive stresses on the bolt holding the turbine cover, which ultimately led to metal fatigue. So on 17 August 2009 at 8:13 a.m., the load on this turbine was 475 megawatt, and that is band number 2, that is not recommended zone. So water flow was 256 meter cube per second, and bearing vibration was 0.84 millimeter, that is 4 times higher than other turbine. So there was a loud bang from turbine number 2 at 8:13. The turbine cover, which weighs 920 tons, rotor then shoot out of its seat. After this, water spouted from the cavity of the turbine into machinery, resulting in flooding of machine hall. Alarm in control room and power output fell to zero, resulting in total blackout. Operators then rushed towards the intake gate, climbed the stairs, and the intake gate, weighing 150 ton, were closed manually by opening valves of hydraulic jack between 8:35 to 9:20 hours. Emergency generators then were started at 11:32, and at 11:50, 11 spillway gates of dam rerouted the river, and during this incident, 75 pupils died. So at the time of incident, 9 out of 10 turbines were operational with a total output of 4,400 megawatt. The turbine had reached 29 years and 10 months, just months away from its design life of 30 years. A survivor of the incident described this as follows: I was standing upstairs when I heard some sort of groaning noise. Then I saw the corrugated turbine cover rise and stand on it. Then I saw the rotor rising from underneath it. It was spinning. I could not believe my eyes. It rose about 3 meters. Rocks and pieces of metal went flying. We started to dodge them. At the time, the corrugated cover was nearly at roof level, and the roof itself had been destroyed. I made a mental calculation. The water is rising 380 cubic meter per second, so I took to my heels and ran for the turbine number 10. I thought that I would make it. I climbed higher, stopped, looked down, and saw everything getting destroyed. Water coming in, people trying to swim. I thought someone must urgently shut the gate to stop the water manually. Manually, because there was no power, none of the protection system had worked. So the damages in this power plant on because of this incident were as below. Turbine number 6 was flooded. Turbine number 5 was flooding and electrical damages. 3 and 4 moderate electrical and mechanical damages. Some damages to the concrete structure around them. Turbine 1, 8 and 10 severe electrical and mechanical damages. Some damages to the concrete structure around them. So turbine number 7 and 9 completely destroyed with extreme damage to the concrete structure around them. Turbine number 2 destroyed completely, including the concrete structure around it. A machine already weakened by time, pushed into an unstable operating zone and subjected to relentless vibration, became the cause of this catastrophic failure.